In the previous video, we described the three-dimensional coordinate system that consists of the x, y, and z axes, and we looked at how to plot some points in that system and how to describe some simple regions. We ultimately will talk about how to describe all planes and all lines in three-dimensional space. It shouldn't be surprising that that will be important. But in order to do that, we actually need to talk about vectors and some vector algebra. And so before we go and do this, we can take a small tangent here and talk about distance in three-dimensional space, because this builds directly upon what we know about how distance is computed in 2 dimensions. So to just kind of quickly review 2-dimensional distance, let's take the xy plane, the standard xy plane, and let's say we have 2 points in this plane. Let's take this point here, which I'll call x1, y1, and I have another point up here, which I'll call x2, y2. Right, and let's say we want to compute the distance between these points. So in other words, I want to compute the length of that black segment that I just drew. And so what we can do in order to find this distance is we can make a right triangle like this. So taking the vertical line from x2, y2 downward and taking the horizontal line at x1, y1 to the right so that they intersect at that right angle. And then we can look at the lengths of the 2 legs of this right triangle. So the leg on the right side of the triangle, that distance there we know is going to be y2 minus y1. And the distance, or the length of the bottom of our right triangle is going to be x2 minus x1. Right, so we can just compute those two lengths based on the x and y coordinates of our 2 points. And so now if I call the distance that I want d for distance, then the Pythagorean theorem tells us that d squared is going to be x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay. And since d squared has 2 square roots, but we only want the positive one since it's a distance, we can take the square root of both sides and again take the positive square root. And so d is going to be the square root of x squared minus x1 squared plus y2 minus y1 squared. Right? And this is our really familiar distance formula from geometry. Right? So it's just based on the Pythagorean theorem. So now when we turn our attention to 3-dimensional space, if we have 2 points in the 3-dimensional coordinate system and we want to find the distance between them, we can generalize this approach. All right, so first off, I apologize for the picture quality here. I know it's not the greatest, but it'll do. I think it'll work for what we want it to do. So in this case, what we have is we have a point here in 3 space that we're calling x1, y1, z1, and we have another point up here that we're calling x2, y2, z2. And the goal is to find the distance between those 2 points, so the length of that segment that connects them. And so what we're able to do in 3-dimensional space is to make a right triangle by forming a rectangular box where the 2 points that we want the distance of are opposite corners. And so that's what is drawn here. And so what can be done is at this point, the point at the top, x2, y2, z2, we can bring that point down, vertical line downward to the bottom of the box. And then we could sketch a line across the diagonal at the bottom of across the bottom of the box. And so when we do that, we form a right triangle. Right? It doesn't look like it in the picture, but the one line there is vertical, and the other one is a horizontal line. It's drawn in that plane at the bottom of this box. And so what we get is a right triangle. And so we can draw the right triangle over here outside of our picture. right? So this point here, this is x1, y1, z1. This point up here is x2, y2, and z2. And the third point, the point at the right angle here, this will have the same x-coordinate and the same y-coordinate as our second point. So it has x2, y2. And that's because we've just taken that point x2, y2, z2, and we just changed the height of the point, which only changes the third coordinate. So the x and y coordinates stay the same, and the z coordinate is now the same as our first point. So that would be the point x2, y2, z1. All right, so now our goal is to find this distance here, that segment. And we can find the distances of the other segments using the two-dimensional distance formula. So this segment here on the bottom, we can ignore the z-coordinate here. The z-coordinate, this segment doesn't move up or down. It moves directly across. So this distance here is just our standard distance formula. So this would be the square root of x2 minus x1 squared plus y2 minus y1 squared. Right? The z-coordinate makes no difference there. It's just like thinking of 2 points in the xy plane, where z is 0. Right? The other side, over here, this one, the x and the y coordinates are still the same. The only thing that's changing are the z coordinates. So this length would be z2 minus z1. So now using the Pythagorean theorem, we can find our desired distance. So d squared is going to be the sum of the squares of the legs. So we're going to have the square root of x2 minus x1 squared plus y2 minus y1 squared. We want that squared plus z2 minus z1 squared. Right? And so we can just take the square root of each of these things, each side. So of course we want the positive square root on the left side. We want d. And we want the square root of all of this. Now notice that in this first term we have the square root squared, and those will cancel each other out. So we're just left with x2 minus x1 squared plus y2 minus y1 squared, and then plus z2 minus z1 squared. So this is our three-dimensional distance formula, and it follows quite naturally from the two-dimensional version. Right? And it looks exactly how you would want. In fact, if you would cover up the z2 minus z1 squared part of this formula, you get exactly the two-dimensional version. So it's just tacking on one extra term in the formula that accounts for the change in z-coordinate. All right, so just to give this formula some formality, let's write it down like this. So we have our distance formula. So if I have 2 points, say P1, which is x1, y1, z1, and I have another point P2, which will be represented by x2, y2, and z2. Then the distance we're going to denote by this notation. So we're going to put the points next to each other, P1, P2, with vertical bars around them, kind of like absolute value bars. And so this will be, by definition, the distance between them. So as we just saw, this will be x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and then the square root of that entire expression. All right, so this is our distance formula that we can use for any 2 points. So for a really straightforward example of this, let's say we were asked to find the distance between point P1, which is going to be given by coordinates 2, 1, 5, and P2, which is given by the coordinates -2, 3, 0. Right, so we have 2 points in 3 space. We want to find the distance between them. Right, and so the formula tells us exactly how to do this. All right, so we subtract the x values and square that. So -2 minus 2 squared. We add to that the difference of the y values squared, so 3 minus 1 squared, plus the difference of the z values, z minus 5 squared. And so we go and we just compute what all of this is. So -2 minus 2 is -4. We square that to get 16. 3 minus 1 is 2. Squared is 4. And 0 minus 5 is -5. Squared is 25. And so we get the square root of 45. So these 2 points in 3 space are exactly the square root of 45 units apart. Now that we know how to compute distances in 3 dimensions, we're able to talk about regions in 3 space that are defined by distances. Right? So one such instance of a region is a sphere. Right? Now everyone probably has an intuitive idea about what a sphere is. You think of it as a perfectly round ball kind of shape. But we want to think of this in terms of 3-dimensional geometry. So the way that we can think of a sphere in 3-dimensional geometry is that it's going to be the set of all points, x, y, z, so all points in 3 space, which are a fixed distance That fixed distance we're going to call r, which obviously stands for the radius of the sphere. So it's a set of all these points which are a fixed distance r from a fixed point, which is the center of the sphere. Okay. And so this is how we want to think of this, is all these points that are a fixed distance from a fixed point. And so if we kind of play around with this, it's not too hard to see that if I want to find the equation of a sphere, with radius r and a center which is the point HKL. Right, so just using those 3 letters to denote my fixed point, the center of my sphere. This equation is going to be x minus h squared plus y minus k squared plus z minus l squared equals r squared. Right, so this is my equation of a sphere with these properties. And this makes intuitive sense once we look at it. If I would take the square root of both of these both sides of this equation, the square root of the left side is simply the distance from the point xyz to the point hkl. And on the right side, when we take the square root, we would just get the positive value r. And so this equation is quite literally saying the distance from xyz to HKL is equal to r, which is exactly the definition of sphere at the top of the slide. Right? And so every sphere with radius r and center HKL can be written in this form. And once it's written in this form, we can quite easily see what the radius is and what the center is. So let's look at the following example. Let's say I wanted to find the center and the radius of the sphere given by the equation x squared plus y squared plus z squared plus 3x minus 4z plus 1 equals 0. Right? Now, your first reaction to this might be that this is not an equation of the sphere as I just had written down on the previous slide. Right? And of course, you're correct that it's not in that same form. However, it doesn't mean this is not a sphere. It just means it's not written in that sort of standard form that quite literally gives us the radius and center. And so what we need to do is we need to rearrange this equation so that it looks like the x minus h squared plus y minus k squared plus z minus l squared equals r squared. We need to rearrange it to get it into that form. And so what we can do is first start by putting all of the x's, the y's, and the z's all together with similar terms. So I'm going to put all the x terms first. So I'm going to have x squared plus 3x. And then we'll have y squared plus y squared. And then we'll put the z terms, z squared minus 4z. And I'm going to go ahead and move all the constants onto the other side. So that's all going to equal -1. All right, so this is just algebra, just rearranging things. And now what I'm going to do is, because I want, if I look at just the x terms, here I have x squared plus 3x, right? And I want something like x minus h squared. I want to get a perfect square out of this. Well, when I have something, but it's not a perfect square, like in this case, but I want to make it a perfect square, we have an algebraic technique to do that. It's called quite literally completing the square. And so as a reminder of how that works, if I have something like x squared plus 3x, I'm going to take the coefficient of the single power of the variable. So in this case, the coefficient of 3x, which is 3. I'm going to divide it by 2 and square it. All right, so 3 divided by 2 is 3/2, and then I square it and I get 9/4. And then I'm going to add 9/4 to both sides. All right, and so what we're going to have here, we're going to do this for each of the 3 variables. So for the x's, we're going to have x squared plus 3x, and then I'll use a different color here. By completing the square, I'm going to have to add 9/4 over here, right? And on the other side over here, I'm also going to add 9/4. So right now, this equation hasn't changed. We've just added some number to both sides of it, and that's okay. The y term, as it is, there's no other y terms. It's just y squared. So we're not going to do anything with y, with the y term, because we already have y squared. We already have a perfect square. And then for the z terms, we're going to need to add a constant. So I have z squared minus 4z, and we need to add a number here. So I take the coefficient of the z term, which is -4. I take half and square it. So take half is -2, square is 4. So we're going to add 4 to both sides as well. Right, so this is just completing the square. It's something from high school algebra. And this allows us to write this equation in the form that we want. These first 3 terms are now form a perfect square. It's x plus 3/2 quantity squared. Y squared is a perfect square itself. If we really want to get it in the right form, we can think of that as y minus 0 squared, although certainly y squared is sufficient. And the last 3 terms we can write as a perfect square. This is going to be z minus 2 quantity squared. And this is all going to equal -1 plus 9/4 plus 4. And that is equal to 21/4. Right? And so from this form, we can just read off what we want to know. So the center of this sphere is going to have coordinates -3/2, 0, and 2. And the radius is going to be the square root of 21/4, which, if we wanted to simplify a little bit, would be the square root of 21 all over 2. Right? And so anytime we have a sphere, we can always use completing the square to get it into this, what we might call standard form, and then read the center and radius off from that form. The last piece, the last little tool that we need relating to distance in three-dimensional space is the idea of midpoint of a segment. Right? So the midpoint of the segment between a point P1, which will be x1, y1, z1, and P2, which will be naturally x2, y2, z2. The midpoint of that segment will be given by the point x1 plus x2, all divided by 2, y1 plus y2, all divided by 2, and z1 plus z2, all divided by 2. Right? Now, intuitively, this makes sense. What we're really doing in each of the coordinates is we're averaging together the two coordinates. Right? So if the one point has an x-coordinate of 3 and the other has an x-coordinate of 9, halfway in between 3 and 9 is 6. It's the average of 3 and 9. And if we do that in each of the three coordinates, the point that we land at will be halfway between our starting point and our ending point. Right? Right? So we can use midpoints as well as the distance formula in the formula for spheres that we just talked about to answer all sorts of different kinds of questions. So, for example, let's say I wanted to find the equation of the sphere whose diameter has endpoints uh, 2, 1, 4 and 4, 3, 10. All right, so in order to write down the equation of the sphere, I need to know two things. I need to know the center, and I need to know the radius. And I'm not given either of those things directly, although we can pretty quickly use what we know to figure out those two things. So I'm given the endpoints of the diameter of a sphere. Now the endpoints of the diameter are going to be points on complete opposite sides of the sphere. And so if you think about how a sphere would work, the center of my sphere will actually be the midpoint of these two endpoints of the diameter. So it'd be the midpoint of 2, 1, 4 and 4, 3, 10. Right? The center will always be the midpoint of two ends of a diameter. And so we can compute this using the midpoint formula. So this will be 2 plus 4 divided by 2, 1 plus 3 divided by 2, and 4 plus 10 divided by 2. And so this looks like we get 3, 2, and 7. So our center of our circle will be the point 3, 2, 7. And then the radius, there's actually a couple different ways we could find our radius distance. The first way is we could find the distance between the two endpoints that were given, so between 214 and 4310. That would give us the length of the diameter of the sphere, and we could then divide that by 2 to get the length of the radius. What we could also do, now that we know the center, we could find the radius directly. Right? It's going to be the distance from either of our endpoints. Doesn't really matter which one we pick. I'm going to pick the first one, 214, just because the numbers are smaller. Right? It's a distance between our endpoint 214 and the center 327. That's by definition the radius, the distance from the center to a point on the sphere. And so r is going to be the square root of 3 minus 2 squared plus 2 minus 1 squared plus 7 minus 4 squared. So that's going to be the square root of 1 plus 1 plus 9, and that is square root of 11. Right? So then we have our center, 327, and our radius, square root of 11. So the equation of our sphere is going to be x minus 3 squared plus y minus 2 squared plus z minus 7 squared. And it has to equal the radius squared. So it's going to equal 11, not square root of 11. Right? And there is the equation of our desired sphere.